Assalamu alaikum students. Welcome to Slate. This is me, Khawaja Yasin. Let's study chemistry. In the last video, we talked about a very important chapter of O-level and IGCSE chemistry, which is acid, bases, and salts. As I mentioned, that the topics, the equations, and the concepts from acid, bases, and salts will be covered in other chapters. You will be getting questions regarding those particular reactions in various chapters. So that is why this is a very important chapter. In the part 1 of this lecture of acid, bases, and salts, we just covered acids. The properties of acids, what are acids, the reactions of acids, the classification of acids. Now, in this video, we are going to talk about bases and furthermore pH and indicator and lastly oxides. So let's start the chapter. Let's start this video with the topic of bases. Now, what are bases? A very easy way to understand bases, if you have to define them in the exam, bases are the oxides or hydroxides of metals. Bases are the oxides or hydroxides of metals. So when you see there's a metal out there, any metal, calcium, barium, magnesium, iron, and you see an oxide of that iron, oxides, for instance, if we call it calcium oxide, know that calcium is in group 2, therefore calcium will have a +2 charge. Oxygen is in group 6, hence -2. So these two will cancel out each other. Calcium oxide having O-2 at the end is a base. Likewise, Na2O, because sodium is +1, oxide is -2, the crisscross method, and we end up getting Na2O, sodium oxide. So this is also a base. And the hydroxide, they contain OH- group. So Na is plus, OH is -1. You cancel out the charges, and you're at the end left with NaOH. That's a hydroxide. Likewise, for calcium hydroxide, hydroxide is -1, calcium is +2. Since it's a polyatomic ion, it's a complex ion, we'll obviously crisscross the charges. 2 will go here, 1 will come here. But for a polyatomic ion, we use the brackets, and we have discussed that in the other videos as well. So this will be the formula of calcium hydroxide. So what are bases? Bases are just the oxides or hydroxides of metals. Now, there is a very important concept here at play. Alkali. Alkali is a type of base, but what type of base? Alkali is a water-soluble base. Any base which is soluble in water, we have discussed the solubility rules in the other video. So remember, any base which is soluble in water, that is an alkali. So for that, you need to memorize the solubility rules, which will be in the part 3 of this video. So now, which ones are those? For example, sodium hydroxide, magnesium hydroxide, calcium hydroxide, mainly group 1 and group 2. Potassium hydroxide, these are water-soluble bases. So when you put them in water, what do? So alkalis, just like acids, they ionize in water, giving hydroxide ions, OH ions. So remember, what was an acid? A proton donor, NH plus ion donor, a hydrogen ion donor. Just like that way, a base, an alkali, especially an alkali, is an OH ions donor. Remember, all bases do not give hydroxide ions. One thing that you need to remember, all alkalis are bases, obviously, because they are a type of base, but all bases are not alkalis. So remember, all alkalis are bases, but all bases are not alkalis. So then if you have a metal oxide, oxides are insoluble except sodium and potassium. That will be discussed in the solubility rules in the next video. So apart from that, all oxides are insoluble. So they are bases, they can never be alkalis. And on that basis, there are different procedures of their reactions in the preparation of salts that you will be studying in the next video. So now let's discuss the type of alkalis. Just like acids and acids, when we talk about bases, and as I said, they also ionize in water. For instance, sodium hydroxide will ionize in water, giving Na plus and OH minus ion. Likewise, calcium hydroxide will also ionize in water, giving calcium plus 2 ion and 2 moles of hydroxide ion. So just like acid, they also ionize in water. So these are alkalis. So let's talk about the types of alkalis. First, strong alkali. Which is a strong alkali? Just like acids, an alkali that dissociates or ionizes completely in water is a strong alkali. For example, we can talk about the examples we just did here. You can look at these examples that sodium hydroxide is an alkali. I put that in aqueous medium. We get ions. Likewise, calcium hydroxide is an alkali. It's the same thing. So that is what you need to know about alkalis. Strong alkalis dissociate completely in water. What about the next one? Obviously, if you are talking about a strong alkali, there must be a weak alkali as well. Simple. If you remember the definition of strong and weak acids, if you have seen the previous video, you would know an alkali that dissociates. I will change the color here for your memory. Partially in water. And one good thing about that, remember in the last video I talked about how you need to remember the strong and the weak acids. You need to memorize them. So for weak alkalis, it's a very good thing. There is only one example in your syllabus, and that example will always be there in the exams. And that is ammonia. Now there it's a little different. Remember what I said. What are bases? Bases are the oxides or hydroxides of metals. But what is ammonia? NH3. There is no metal, there is no oxide, there is no hydroxide. Then why is ammonia an alkali? Because when you dissolve ammonia in water, a reaction will take place. You will get NH4 plus OH minus ion. NH4 is it's an ammonium ion. And remember, all ammonium salts, where ammonium is present as a cation, they are water soluble. Anyhow, so ammonia is a water soluble base. This is water as a liquid. So this is ammonium ion and this is hydroxide ion. So what was the definition of alkali? That dissociates in water or that gives OH ions or hydroxide ion in water. So ammonia is a base. Ammonia is an alkali, but it's a weak alkali or a weak base. So what do we conclude from here? What are bases? Bases are also called proton acceptor, and furthermore, OH ion donors. Now, why are we calling bases a proton acceptor? Let's see. From there on, we're going to talk about the properties of bases. If they say that a base is concentrated or a base is dilute, what do they mean there? Just the same thing, like acids. That more amount of base is in water, strong alkali, concentrated alkali has more alkali in water, and dilute alkali has less alkali in water. It's the same way in acids. It's a solution. So now let's jump to the properties. First, they accept proton. We just discussed. Protons are hydrogen ions. Remember that. They have a pH more than 7. And pH range is from 7 to 14. So a base will have a pH range of 7.1 to 14. And 14 will be a stronger base, which we will be discussing in the next topic of pH. Now, students, there's another important property of bases that you need to remember. They turn red litmus paper blue. So the end result of a red litmus paper in a base, in an alkali, when it's dipped there, it turns blue. So when I was a student, how did I remember that? I only remembered this property, not the property of acid. I remembered, okay, B for base, B for blue. So that's the base one. For acid, the left one is red. So acids turn blue litmus red, bases turns red litmus blue. But the important property, bases with acid. It's the exact same reaction that we discussed in acids. So whenever we react an acid with a base, that's called a neutralization reaction. Because bases are highly corrosive. Just like acid. They can also damage your skin, they can also damage your eyes. So acids are corrosive, bases are corrosive. But when we mix them together, that neutralizes it. That neutralizes the pH as well. So that's a neutralization reaction. A base with an acid is always a neutralization reaction. So let's take any base. Calcium oxide with HCl. So calcium oxide is a base, it's not an alkali. So we get H2O, which is water, and calcium chloride. So that is what is happening here. So what did I tell you? A base is a proton acceptor. So this acid is giving out a proton, this proton, because acid dissociates in water. These are both in aqueous medium. So this acid will give a hydrogen ion, and this base will accept it and turn it into water. So that is a neutralization reaction where we get salt and water. Likewise, if we take calcium hydroxide, this is an alkali, and let's say we take H2SO4. Let's make it a little different. So the base will again accept these hydrogen ions from H2SO4, which is sulfuric acid, and form 2 moles of water, and the salt will be calcium sulfate. So this is also a neutralization reaction, students. Now, this is one reaction of bases, but there's only another reaction. Alkalis with ammonium compounds. So alkalis with ammonium compounds. This is a very important reaction, just like the metal carbonate reaction with acid. Remember, acid plus metal carbonate gave us carbon dioxide plus water plus salt. And the carbon dioxide was the main product. Carbon dioxide, which turns lime water milky, tells us that some particular reaction has happened. In this case, we take an ammonium compound. For instance, ammonium is +1, chloride is -1, ammonium chloride plus sodium hydroxide. So what will happen here? Apparently, students do that. It's a common mistake. They do a displacement reaction, exchange two things. For instance, they would just do it like NaCl plus ammonium hydroxide. There is nothing wrong with the equation. But for your syllabus, you need to remember that whenever an alkali reacts with an ammonium compound, ammonia gas is liberated. So do we see any ammonia gas in the equation? Not at all. So we are going to separate it out. We get ammonia, which is a gas, and water, which is a liquid. In NaCl, it's an aqueous salt. So aqueous. So here we get salt plus water, but the main product is ammonia gas is liberated. And how do we find out that it's the ammonia gas? There are two ways. A, it has a pungent smell. By pungent, we mean it's a very sharp smell. If you smell it, you will feel something here sharp, like just like a needle has hit your nose. It's that sharp. So that's one qualitative test of ammonia. But the important one is, since it's an alkali, what will it do? It will turn damp red litmus blue, as that's the property of alkalis and bases, that they turn red litmus blue. So that's what ammonia is going to do. So that's what's happening here. So these are the two important reactions. Remember, acids and bases that we've done, neutralization, but alkalis with ammonium compounds, any compound which contains an ammonium ion. So this is an ammonium ion, NH4. So any compound that contains an ammonium ion with alkali will give us salt, water, but ammonia is the main one, ammonia. And since ionic equations are very important, we will be discussing that properly in the next video. But let's talk about an ionic equation of neutralization reaction. That's a very important one. For example, we take calcium hydroxide plus HCl, the one we did up there. Aqueous, this is aqueous. You will find that in solubility rules. For ionic equation, solubility rules are very important. Now, what do we get? An aqueous calcium chloride plus water as a liquid. So, know for the ionic equations, only the aqueous compounds are ionized or dissociated, just like we did. So, how will calcium hydroxide be dissociated? Calcium +2 plus OH -2. And how will HCl be dissociated? H plus and Cl minus. How will calcium chloride be dissociated? And water will not be dissociated. So we cancel both these out, which are being repetitive. We cancel calcium with this calcium. We cancel these two chlorides with these two chlorides. What are we left with? Two OH minus plus two hydrogens will give us two waters. We cancel out the twos from all the sides, and that's the equation that we are left with. So students, why am I doing it? Because whenever in the exam, they ask you to give the ionic equation of a neutralization reaction, that whenever an alkali is reacting with an acid, you do not need to do all these steps. Just write this equation. Hydrogen ion plus hydroxide ion gives water. That is the ionic equation of a neutralization reaction. So that is all about bases. But as I said, bases are the oxides or hydroxides of metals. So from there on, let's discuss a very important topic again, oxides. Oxides are anything which contains oxide ion, O-2. It's in any salt, but there are 4 important types, and their periodic table will play an important part. We will do a past level question here as well. So at first, as I told you, we're going to talk about, we have 4 different oxides. So let's make 4 columns. Acidic oxide, basic oxide, amphoteric oxide, and neutral oxide. Now, about these oxides, what are acidic oxides? Simply, there are various points of these oxides. They can be differentiated. You can get a question of differentiation, or you will get a periodic table. So, acidic oxides. What are acidic oxides? These are oxides of non-metals. Oxides of non-metals. That's it. It's that easy. If oxide ion is there with a non-metal, that's an acidic oxide. But what are basic oxides? Oxides of group 1 and group 2 metals, which is alkali or alkaline earth metals. What are those? We can write it down there for you. Obviously, rubidium and cesium, they do not react. So we only talk about lithium oxide, sodium oxide, or potassium oxide. Likewise, beryllium, magnesium, calcium, strontium, and barium. So oxides of these elements, group 1 and group 2, these will form basic oxides. Amphoteric oxides, by amphoteric we mean contains properties of 2 different things. So these are the oxides of transition metals or metalloids. Now, going back again to the acidic oxides, they are gaseous in state. These are mostly solids. And these are also solids. So acidic oxides are gaseous or can be liquid, but these are solids. Now, the important property, the most important property. Acidic oxides form acid when dissolved in water. The examples can be, for example, carbon dioxide, phosphorus oxide, nitrogen oxide, sulfur dioxide. So students, these are the examples. What can we do? As I'm saying, if we add them in water, they form acids. Do they? Let's see. So if I add calcium carbon dioxide in water, what do I get? H2CO3, which is carbonic acid. If I add phosphorus oxide in water, decoxide, we get phosphoric acid. From here we get nitric acid. From here we get sulfuric acid that you will be studying in contact process as well. So as you have seen that all these acidic oxides in water gives acid, and when this acid reacts with alkali, it forms salt in water. So that is what you need to know about acidic oxides. Now, what about basic oxides? They form alkali when dissolved in water. So let's talk about the examples of basic oxides, various oxides. Na2O, sodium oxide, potassium oxide, calcium oxide. And when I dissolve it in water, what do I get? I will get calcium hydroxide, an alkali. Sodium hydroxide, another alkali. Calcium hydroxide, another alkali. And these alkali, when they react with acids, they form salt and water. I'm sorry I'm repeating it again and again, but neutralization is the most important reaction of O-levels chemistry, especially for P4 and P1 and P2 as well. Now let's talk about amphoteric oxides. As I said, amphoteric contains the property of both. So what will they do? They react with acid to form salt plus water. So that's the property of a base. But furthermore, they react with alkali to form salt and water. So they behave as both. So that's why they are amphoteric oxides. The examples that you need to memorize are zinc oxide, aluminum oxide, which is a metalloid. Aluminum is a metalloid, and iron oxide. So these are very important examples. Now, we do not need to do their chemical reactions. They're not in the syllabus that much. Lastly, the neutral oxides. These ones are the ones that you need to memorize. They're neutral, so they neither react with acid nor base. They don't react with them. There are 3 examples of that. And the most important element, a compound with oxygen in it, that's a neutral one, which is water is a neutral oxide. Carbon monoxide. Here we had carbon dioxide as an acidic oxide. But carbon monoxide is also a neutral one. And nitrogen monoxide. These 3 are neutral oxides. So that is what we know about oxides. There are 4 types of oxides: acidic, basic, amphoteric, and neutral. Last part of the video where I said we will be talking about pH. Students, this is not the power of hydrogen. pH determines the acidity or alkalinity of any solution. So the pH that we have been discussing in the previous parts will tell us that if a solution is acidic or alkaline or basic. So pH is, it's actually, what it actually means is negative log of hydrogen ion concentration. But that is not in your syllabus, so ignore that. Don't take my cross as that it's a wrong one. pH is the negative log of hydrogen ion concentration. That's a quantitative calculation, not in O-levels. But qualitatively, pH has an important part. As I said, Remember, pH is a numeric value. So pH has a ranges from 0 to 14. So 0 to 6.9 is acidic, where lesser the pH, stronger the acid. So an acid with 1 pH is stronger. An acid with 6 pH is weaker. So that's how it goes. Similarly, for bases, it's 7.1 to 14, but it goes in the other direction. So 8 pH is a weak base, and 14 pH is a strong base. And what about 7? 7 is equal to neutral. And the example for 7 is the water. Water is neutral. Not the rainwater, not the drinking water. Drinking water is alkaline, rainwater is acidic, but distilled water that we use in labs, so that it doesn't change the pH of the solution. So now, let's see a pH chart. Now look at this chart. This can help you understand and remember it. So this is pH 0, and there we see dilute HCl. Remember, HCl was a strong acid. We go further to lemon, citric acid. It's comparatively a weaker one. Vinegar, acetic acid or ethanoic acid, going weaker. Fizzy drink, carbonic acid, weaker. Then rainwater, which is acidic rain that you will be studying in the next chapter, in the last chapter. Rainwater is also acidic. Milk, lactic acid. By the way, rainwater contains H2SO4 and HNO3, but in very small concentration. So milk is lactic acid. At 7, what do we see? Pure water. Pure water is at 7. That's neutral. Now, we're going further. So remember, from 7 to 0, the strength of acid increase this way. Lesser the pH, stronger the acid, or more acidic it is. Then 7.2, it's blood. 10, toothpaste. Detergents, 11.2. So you can see that even the cleaning action, they're that strong that they're even used as a floor cleaners as well, which is they're further stronger than detergents. So more the cleaning action, more basic it is. And lastly, at 14, it's dilute sodium hydroxide, which is a strong alkali. So even the strength of alkali also increases, but on the other direction. More the value, more basic it is. Lesser the value, more acidic it is. So strength of base. Now, how do we calculate pH? There are various ways. How do we find out that if a solution is acidic or basic? We use indicators. What do indicators do? Determine the acidity or alkalinity of a solution by change in color. So students, an indicator will have a different color in acids and a different color in bases. So that is how an indicator will tell us that if a particular solution is acidic or basic. So one indicator that we talked about was litmus paper. That's a two-color indicator. We call it a two-color indicator. We don't need much information. It will just tell us that if it's acidic or basic, the strength does not matter. The pH's value does not matter. So what will happen? By now you should memorize it. You should remember it. A litmus paper in acid, which color does it give? Red. And in base it gives blue color. Two other important ones are phenolphthalein or phenolphthalein and methyl orange. These two indicators, we just add drops in the solution and we find out about the colors. So phenolphthalein is purple in color itself. But when you add it in acid, it turns colorless. And what about bases? It turns pink. So phenolphthalein, which is a purple colored solution liquid, when you add drops in acid, there is no color, it's colorless. When you add drops in base, it's pink. And methyl orange, it's orange as the name goes. Red in acids, yellow in bases. So you add a few drops. If the solution is acidic, it will turn red. And if the solution is basic, it will turn yellow. Because the solutions, they don't have any color beforehand. So that's why we add indicators. That's why we check it through that way. So these are just two color indicators. But we can also find out about the range of pH. For example, for that we use universal indicator. So about the universal indicators, you add drops and then you match different shades. They have a shade. You will get a shade card with it. Let me show you that. You add the drops in the solution, you can get various colors. And those colors will tell you the pH. Now look at this. If the pH is 0 acidic, it's brown. If it's red, it's 1. 2, pink. 3, orange. It's like rainbow colors. 4, beige. 5, yellow, lime green, green. It gets darker, turquoise, pale blue, blue, dark blue, violet, purple. So we just match the shade card with the solution and we find out if it's neutral, that's green, what is the pH. But do we get the exact pH? No, it will just give us the pH value of pH is 1, pH is 8. But pH values are mostly in decimal. 1.8, 2.7. For that we use pH meter. It's just like a digital thermometer. You dip the pH meter in the solution and it is connected to a computer or can have a digital meter on its top. So when you dip it in the solution, the exact value of pH will come in front of you. For instance, we saw in the case of blood it was 7.2 or 3. So 7.3. The universal indicator cannot give me that value. It can only tell me it's 7. But the pH meter will give me the exact value, 7.3. So that is how you calculate the pH. Through two color indicators, through the universal indicator, which is the shade card, or through pH meter. So in this video, we talked about bases, oxides, pH and indicator. And in the next video, in the last video of this chapter, we will be talking about the solubility rules, the ionic equations, and the preparation of salts. Very important for all P1, P2, and P4. So thank you so much, students, for being here with me. Allah Hafiz.